Get started. I know a number of you have an exam across campus at 10:10, so I'll try and end a few minutes early, and if I'm forgetting, somebody wave a hand or get my attention somehow. Okay, so we left off talking about databases. So what I'd like to spend some time doing today is going ahead and showing an example of accessing a database in R. Actually, if you guys can do that after class, if you don't find it in the next second, thanks. So let's go through an example of accessing a database through R and doing some queries, and then what we'll do is we'll transition to using a package in R that allows us to read in a very large data file and do analyses on a very large data file. Okay, so the basic idea is sort of like with what we saw with for each, that there is the DBI package, like the for each package, is basically a front end, and on the back end, in terms of the systems level stuff, there are different back ends that can connect with different database management systems. So the nice thing is that regardless of what kind of database what kind of software is managing the database on the back end, we can use the same sort of commands from R to interact with that database. So I mentioned that SQLite is a nice lightweight database that doesn't involve having to contact a server and do authentication. You just have a single file on your local machine and work with the database there. So that's the example we're going to use. And we're going to work with this bibliographic database that I mentioned last time, which is basically most of the statistics and related journal articles over the last 100 years. So if we look at the schema for that database, it looks something like this. And I often find it helpful to sort of write things down so I can have them written down in front of me to be able to see things. So the way that I was able to sort of see that this is what things look like is as follows. So I'm going to load in the R SQLite database package. And you'll notice that's loading DBI, which provides this front end. So this is dealing with the back end stuff of interfacing with an SQLite database. And then I'm going to give it the name of the file. So the database is just in a single file, even though it's a bunch of these tables. And I'm going to tell it that the driver, sort of the back-end setup, is SQLite, and then I'm going to connect to it. So we're using another one of these things called a connection, like you guys have already seen. So we're going to connect to it, and then we're going to be able to refer to the database as this object DB, henceforth, in doing our queries. Okay, so any questions about the setup? Okay, so now we can use some functions in R to basically get some information on what's called the schema, sort of the layout of the database. So
are you working on SDF machine or you are?
Oh yeah, excellent question. So I am working on Arwin, and the file is actually on the SCF file system here. Okay. And this particular drive is available from all of the SCF machines, so you could do this on any of them if you want to play around with it. Okay, so it lists out the different tables. They're the sort of things that you might imagine. There's a table that has article information, there's a table that has information specific to the journals, authors, authorships, etc., etc. And we can then say, well, what are the fields in some of these different tables that look like they might be useful and interesting to us? So if I look at the articles field, for example, it says, okay, there's an ID. This is presumably a unique ID for the different articles. There's a title, there's a volume, there's a journal, and then there are a bunch of ID fields that are going to allow us to associate information in this table with the information in the other tables. So these are unique IDs. These are these foreign keys that are going to allow us to make the connections and the merges with the other tables. You'll notice the authors field is pretty simple. It's just an ID and then the actual name, so there's not much going on there. And then the authorships, this is sort of what deals with the fact that any given article could have sort of an arbitrary number of different authors. So it has both an ID field for the table, it also has an ID for each individual title, and an ID for each individual author. And then proceedings and whatnot. So if you start to think about what this means in terms of what are the fields I'm going to need to do the merging on, what are the foreign keys that I'm going to need to do the merging on, things look sort of like this. So we can relate between articles and authorships with this ID title field. And we can get names of authors as opposed to just their IDs by going from by connecting to the authors table and looking at the author ID field, and that is equivalent to the ID field in this table. And then if you think about authorships, then the sort of things that you would see here is a bunch of repeats, because you could have the same author for different. So if this were the author and this were the ID of the title of the journal article, we could have the same author on different titles, and we can have different authors on the same title. So that sort of deals with that aspect. That's how they decide to set things up to deal with that aspect of things. Okay, any questions? So you can imagine if you think about bibliographic information, you might just want to do something simple of like bringing the name information from the authors into the articles information that has most of the information on a given article, so that you could sort of see what's the full bibliographic entry for any given article. Or you might want to say, okay, for a given author, I want to go look for all the articles that author was involved in. So to do that, we're going to need to do some joining across the different tables. And what I thought I would do here is just show a few examples of some of the different ways you can do these things. And there are lots of different ways to set this up. So the first thing is we could just basically pull an entire table into R, or pull a piece of it into R. So we can do a query. We can send a query to the database, and in this case, this is using SQL this is using SQL syntax, and it has keywords like select and where and from that will that allow us to do the different queries. So let me go back to the PDF. So I'm not going to do this in sort of a structured way, but basically the way that SQL queries look like is select some fields, or a star for all the fields, from a given table. And in some cases, as we'll see, this will be from joining across multiple tables. And then we can include a subsetting operation with where, and some condition that says, only pull out the rows where the latitude, if its geographic data is greater than 80, or where the name is this, or where the company is in some set of company names, etc. So that could be the subsetting. And there might be some Boolean logic in here as well. And we might want to have the result be ordered on the basis of some other field. So those are the sorts of that's the sort of functionality that we end up mixing and matching when we're doing these sorts of queries. Okay, so here I'm doing a very simple query. I'm basically selecting everything from a given table, so there's not much to that. And I can send the query, and that'll basically do the query, and then that doesn't immediately return everything back into R. And to do that, I can then do fetch and say, how many records do I want to return? Okay, so fetch 5 records from this particular query. And we should then see what looks like bibliographic information. In this case, there's a lot of just IDs in here that are a little bit that is a little bit difficult to interpret as sort of human readable information, but that's what we see there. I'm not sure why R is making me do this, but I need to do that clear result in order to do other queries. So I could also just start to do somewhat more complicated queries. So here I'm going to select the ID field from within the authors table, where I'm only pulling out the IDs that have a name, and here's a regular expression-like syntax to pull out any name that looks like Leo Bryman, who was a faculty member in statistics here a number of years ago. So this is going to match anything that's Bryman, Leo, Bryman, L, all the sorts of things that you run into in querying by name. And that's going to then give me back the IDs associated with this author. So we can see there are two. I believe this is because one of them has his whole first name and the other has his initial, or maybe it has his middle initial, or those sorts of ambiguities. So we're pulling out this information from the authors table. Okay, and then to set it up to then use that to pull information out of the authorships table, I'm going to do a little bit of monkeying around with the list information in R. And then I'm going to construct an SQL query just with paste in R. So I'm just working with text and pasting together what I need to do to create the query that I want to create. So basically what I want to do is from the authorships table, I want to pull out the title IDs for those cases that correspond to the Bryman articles. So where the author ID is in, and here I'm going to construct a string that allows me to take the information from the R object and inject it into the SQL query. Okay, so this is what my query is going to look like. It's got some question marks in it, and that's where these two ID values are going to get inserted in. And they're going to get inserted in by writing a query like this. And if I just do get query, you notice before I had done send query and then fetch, the get query basically combines those two operations and says, go do the query and then return the results back. So I'm going to do the query on the database with this particular string that I've just constructed, and then I'm going to use the R object to fill in for those question marks that got put in there. And then if I return that, then I can go ahead and look at what I get back. So TIDs is a whole bunch of these IDs. So he was involved in a bunch of different articles, and those were just the first 5 of them that I have here. And as we're probably not too surprised to see, okay, I was about to say it's probably a list, but in fact it's a data frame. Okay, and then this is just sort of doing the next step of basically I'm trying to take, since the only way I can grab Bryman out by name is from here, I then need to go from here to get the titles out, and then to get the, then from the titles I can then get the information from the articles to actually pull out the article information that's associated with the author. Yeah, Moshe?
Why do we need to clear the results before we get back what we don't need to every time we do all these queries?
Yeah, that's a fair question. I didn't actually end up taking the time to figure out why I needed to do this. I just when I didn't do this, it gave me an error message, and I figured out that cleared the error message. So I'm not exactly sure what is going on behind the scenes there. I'm actually, now that as I'm answering that, I'm guessing maybe it has to do with the fact that I sent the query and only fetched back some of the results, and so that query is still maybe sort of sitting there in some state, and I need to tell R basically forget that query. I'm going to move on and do another query, whereas the get query sort of returns everything back as well. So I think it has something to do with that. Okay, so I can play a similar game here of now I'm going to select all the fields from articles where the ID title is in, and then again I'm going to construct a set of question marks, and I'm going to throw into those question marks the TIDs that I returned from up here. So I'm basically just doing the next step to walk my way back to the article information. And then I can, so we've seen that we get data frames back, so I can then do head on the result. So I did the query again with my string. I passed in that list, that set, I forget exactly what, I guess it's in the form of a list now, that list of IDs for the title IDs, and then I pulled out the articles that correspond to those title IDs. And then when I do that, then I start to get stuff back that's sort of more recognizable as more standard bibliographic information. And indeed, these look like, you know, the names of articles that are statistics articles. I won't take the time to do it, but just as a check, I then went to Google Scholar and threw a few of these in there, and indeed these are the ones that are Leo Bryman's articles, just to make sure I wasn't doing anything where I was misunderstanding what was going on with the query. Okay, questions, comments? Okay, there are other ways to do that sort of query, and that seemed a little bit involved of sort of stepping my way through the tables and sort of accumulating the information I needed. So I could actually do a query that involves multiple tables. So here's an example of doing that query. So I'm going to select all the fields from this combination of tables, and now I'm going to have a somewhat more complicated selection statement with where. So I'm going to say where the author's name, so from here, authors.name, is like Ryman, so that's the regular expression query. And the ID in the authors table is equal to the author ID in the authorships table, so that's doing the matching from here to here. And the authorships ID title is equal to the article's ID title, so that's doing the joining from here to here. And if I do that, I should get back essentially the same thing as we just saw. Okay, so it took a brief amount of time to do that query, and you can see we've got all this merged information with the titles, and indeed the name has appeared. So basically we've now got fields that are coming from all three of these different tables. And in fact, if we look at this, it's interesting. It didn't have a problem with the fact that there are actually now ID fields from multiple tables with non-unique field names, and it just sort of put them in. So these first columns here are from the articles table, and then there are fields from the authors table, and then there are fields from the authorships table in here. Okay, another thing we can do is create something called a view, which is basically we're going to sort of create a new table that joins across multiple tables, but we're not actually explicitly going to create a whole new table on the disk. So that's why it's called a view. It's sort of more of an abstract kind of table, but it would allow us to then work with things more easily. So in order to do this, I actually need to modify the database. So what I'm going to do here is I'm going to copy the database, which is read-only from that location on the file system, to /temp on my local machine, which is actually also a reasonably good idea anyway for increasing the speed of the query to have it on local disk. And then this create view is actually going to modify the table itself, modify the database itself. So what is this going to do? I'm going to create a view that is basically, let's see, so I'm creating this view that I'm going to call partial article information. I'm going to select all the fields from a join or a merge of the articles table joined with the full, sorry, got distracted here. I'm going to create a view called full author info by getting all the fields from joining the authors table with the authorships table. And the join is going to be done by relating the author ID column and the ID column in these two tables. So that's basically going to create this new sort of abstract table from having joined these other guys. And I could continue playing this game of then creating another view that joins the articles information with the full author info, which was the view that I just created here, and that would essentially accomplish the same sort of thing as I've done in these couple other ways. And again, you can do things like fetching and fetching only some of the records and so on and so forth. So this would be a way if we didn't want to pull the entire set into R, but we wanted to pull things in sequentially, perhaps because the result was really, really big and we didn't want to have it sitting in memory in R all at once. We could play games with pulling in chunks of the database, or chunks of the information that we've queried and extracted from and are extracting from the database. Okay, any questions about any of that? Okay, so a little bit about joining. So sort of like when we looked at, well, actually, did we? I don't know if we talked about merge in R or not. I think I probably talked about that in the boot camp. But anytime you're merging or joining across tables, there's going to be the issue of what's the mapping between the rows in one table and the rows in the other table. Is it 1-to-1? Is it many-to-1? Is it 1-to-many? Is it many-to-many? So if we are when you're talking about databases, there's a whole terminology for these different kinds of joins depending on the relationships between the observations in one row and the observations in one table and the observations in another table. So if you do something called an inner join, which is the default, and I didn't actually say inner join here, but that's what this amounted to when I just said join there. You're basically only going to take rows from each of the tables that you're joining where there's where you have information in both of the tables. So when we join, if we join sort of all this information and we said, okay, we want, if there, let's see, what am I trying to say here? I guess this would be a case where there probably wouldn't be an author in here who didn't have any articles here, so maybe this is not a great example. But suppose I had a database of people, and then a table of people, and then I had a table of states, and I was joining between people and states. I might have some states for which there were no people represented. So maybe I didn't have anyone from Wyoming because it's a small sample of people, and then Wyoming is a small state. So in that case, if I do an inner join, I'm not going to get any of the information on Wyoming from the state table because there's no matching people who link to Wyoming in the person table. So that would be the effect of doing an inner join. And there might be a person who is stateless, say somebody in the military who didn't have a state associated with them. So I wouldn't, if I did that inner join, I wouldn't get those people who didn't have a state associated with them. If I do a left outer join, then basically the first table, let's say it's the people table, I would include all of the rows from that table, but only the rows from the second table, the state table that had for which there were people living in that state. And if I do a right outer join, I do the reverse. So it's basically a question of which rows am I going to include when I do a join. And if I do a full outer join, then I'm going to return all rows from. I'm going to return all the rows from both of the tables, even if they're not matching. Okay. So that was what I just said here. The last kind of join that one could think about is something called the cross join, which is basically going to do what's called the Cartesian product. So that's basically going to be every combination of all the rows in one table with all the rows in another table. So I think we've seen expand.grid in R, so it's sort of similar to that. So for every unique value in one table, I'm going to combine it with all of the values in all of the rows in the other table, and vice versa. So it's going to make a much larger table. But you can also see that a cross join can give you the same result as doing an inner join. So if I did an inner join, select everything from table 1, joined with table 2, where I've got the IDs matching across the two tables, I could do that equivalently as a cross join between the two tables, and that's going to return all combinations of each of the rows from each of the tables. But then if I select from that only where the IDs match. So the cross join would sort of expand things out and do this Cartesian product, and then the where would only select the matching ones. So these would be equivalent in terms of doing the selection. Okay.
So would there be efficiency issues when you use different ways?
Yeah, I mean, that's right. So that's a good question. And I don't know exactly how this would be done by the database management system behind the scenes in terms of whether one of these would be faster than the other. I mean, you might think, we would sort of think naively that doing the cross join seems like an inefficient way to do it and then do the conditioning. But I don't know exactly what's going on behind the scenes in terms of how this gets processed.
And would that usually be an issue when you assess database?
Say that again?
Would that usually be an issue I need to worry about, or?
That's a fair question, and I don't know off the top of my head exactly how to respond to that. Yeah, so I guess the question is basically how much can we expect that the database management system is doing the most efficient thing without us having to think carefully about it. I mean, I think we would probably want to look into the literature a little bit to try and understand a little bit better what makes for efficient queries. And hopefully at the same time the database system is doing some fairly smart things as well. Somewhat along those lines, we mentioned this idea of keys and to give us uniqueness for have unique values associated with which each of the rows or the observations. There's also this notion of tables having an index. And the basic idea of an index goes back to this question that we were looking at in R of the fact that it's in general much slower to look things up by name because you have to search through all the names versus having an index, so you can just go directly to the location where you in order to pull out the record of interest. So the basic idea with a database is, in order to do fast querying, is you want your tables to have indices, and there are commands that say, okay, I want to create an index for this table using this particular column or set of columns. And if you've done that, then that's going to allow the database management system to do much quicker searching and querying and joining, basically for the same reasons that we talked about in terms of looking up by name versus looking up by index. And if you get into databases, you'll see people talking about sort of the time involved in doing lookup, and this is going to be order of n, the number of entries, if you're looking up by name. But if you then have an index associated with it, you can get either logarithmic time lookup or constant time lookup, because you can basically just go directly to the location of the entry that you want to pull out. So in general, this sort of getting back to Darren's question, this is one case where you'd want to look and see if your tables had indices in order, and if they didn't, you would want to establish indices to increase the speed. And I don't think I'll go through this in any detail, but because oftentimes as statisticians, we're sort of being handed a database and then we're being expected to analyze it or work with it as opposed to creating it. But you can also create a database, and in fact, if you've got data in the form of CSVs or other flat formats, it might be a good idea to set it up as a database and create the tables, and you can do that from either CSV files or from data frames in R using some of these same kinds of functions. Like there's a DB write table, and it uses, it does the sort of things like you would expect. We need to give it the connection, and then we need to name the table and say where it's getting the information from, and then there's information, sort of things like names and headers that we need to give it that information. Okay, so I think that's all I want to say about databases in this context of connecting from R. Any last questions? Okay, the other thing I'll mention here briefly, and I'm not going to go through the syntax in detail, is that Sass is actually quite good at dealing with large data sets and doing subsetting and merging. So some statisticians, including I've done this a number of times, will actually use Sass to basically manage merging of large data sets. And so if you know some Sass, this can be a useful way to go. And in some cases, you could also then do statistical analysis in Sass if you were going in that direction. So I just want to point out here a couple things that we see in Sass that sort of mimic some of what we've seen before. I can actually set up a pipe where I give Sass a set of Unix commands of piping stuff, and then basically read the result of that piping into Sass. So again, combining some of the different kinds of functionality that we've seen before. So here I'm going to read in from this thing that I've named temp, which is actually the result of doing this piping, and then I'm going to give it, the names of the fields of the data set, and I could do some subsetting here too if I wanted to. And then I'm going to read in a second, I'm going to read in from a second file, but again, I'm passing this through a pipe. In this case, I'm just getting rid of some of these /r carriage returns that are at the ends of the lines because these were Windows files. They were created in Windows. So I'm going to read in the second file, then I'm going to do a Sass procedure to do some sorting because I need to do some sorting before merging. And then I'm going to do a merge where I merge two different data sets and create a new third data set. So I'm merging these two guys to create this new merged data set. And you can see I'm doing some subsetting. Then I've got a condition here. This is the name of the field that has the name that's in both of the tables on which I'm doing the merging. So those are the keys I'm using to do the merging. I'm keeping only certain of the fields, et cetera, et cetera. So nothing that's going to look surprising if you think about what you need to do when you're merging across different data tables or data sets. And then I'm doing some more subsetting here, and then I'm outputting to CSV at this stage. So just to show you that all of this can also be done quite readily in Sass as well. Okay, questions or comments? All right, so let me now turn to actually working with very large data sets in R without reading the whole data file into memory. So people have realized that a shortcoming of R in terms of dealing with big data sets is that you have to read everything, that you have to have everything in memory. And so as people have gotten interested in working with larger and larger data sets, folks over the last 5 or 8 years have come up with packages that will deal with this problem. And the basic idea is that the data set gets stored on disk in a clever way such that R can go in and access the pieces of the data set quickly. Okay? So it's not just being stored as, say, a flat CSV file. It's being stored in some binary format that then the software can then go in and grab the data relatively quickly, at least, yeah, in a relative sense. So both the FF and the big memory packages allow us to work with these big data sets, and then there's a big LM package that allows us to fit regressions or GLMs on very large data sets. So those are the basic tools we're going to see here. So here's an example. This is an example you'll see a lot when people who are working with R or statisticians are talking about big data sets. This is a US government data set on airline departure information and times and delays, and it was at this thing called the American Statistical Association Data Expo back in 2009. I think there was some competition to see who could sort of analyze the data in the best way in some context. So you can get the data from here. Luckily, it wasn't a government website, so I was actually able to get it a week ago when I was grabbing it. So it's about 12 gigabytes if you combine it into a single CSV. And if we look at the, where's my, there we go. Okay, so I didn't actually include this in the PDF, but you can just see, what I used to do the downloading, just some of the same tools that we saw in the first unit. I used curl and I used the for loop to automate and loop through and download individual CSVs for each of these years. They're in a zip format, and so then in order for FF, the package in R, to read in, it needs them all in one big CSV file. So then I went through and I unzipped them, and I concatenated them all into a single file here that I'm calling airline data all.csv. So that's this 12 gigabyte file. It's not stored in any particularly efficient format because it's just a flat CSV file. So the 12 gigabytes is in some way a sort of an overestimate of how big this data set is because it's not stored very efficiently. This Python script for doing some formatting was if I were going to do an example using big memory instead of FF, but I didn't actually end up using this, so I think I'll just comment that out. And then just to point out that it looks like I left off the names of the actual file, the name of the file here. But one thing that I then did that took a little bit of time okay, so the data are on /temp on Arwin. So I was doing things to try and explore what the values of some of the different fields were. Whoa, that was interesting. Oh, okay. So I was again playing around with some of these Unix utilities where I was doing things like, well, okay, I want to know what the unique values are in some set of fields, so I know if they're integers or are they going to be factor level variables, or when I read them into R, what sort of format should they have. So there might be a better way to do this, but this was what occurred to me was, okay, let me take the big file, cut it based on a comma, and grab out an individual field that I want to look at. And then let me sort it and pull out the unique values, and then I'm going to pass that to less to then just page through those values. So this gives me a sense. It takes a little bit of time, but given that the fields are, each of them is quite large, maybe not too long in context, it gives me some idea of what kinds of values are in each of the different fields. So I did that. I guess we can let that go in the background. And then the other thing that I did, and this is sort of good practice when you're sort of working with new functionality and when you start to work with big data sets, is I created a little test CSV that was just a small subset of 10,000 rows of that initial large CSV. And the reason was that as I was trying to explore the functionality in this FF package and in the big LM package, I was finding I was making a lot of errors in terms of how I was doing things. And the problem is if you make an error in working with a very large data set, you sit there waiting for the error message either to keep scrolling over the screen thousands of lines of information from the error message, or it just takes a very long time to realize that you've gotten the wrong result back. So in this case, in that sort of context, it's a good idea to have a small test case to do the coding on and practice on. So that was one of the things that I did here. Okay, so I won't actually run this because some of this takes a fairly long time, but I'll just show you the code that I was using. So I loaded in FF and this FF base package, which is an affiliated package for some of this functionality. And then I was doing things like the following. Either with my test data set or with the full data set, I was using something called read.csv.ffdf, which stands for FF data frame. So it's they sort of mimic the idea of having a data frame, but it's in this format that deals with big files. So the idea is that you can think about this object that you get back as being a data frame. It's not actually stored in the way that our data frames are usually stored. It's sitting on disk, and the access mechanisms are very different. But you can think about interacting with it in ways that as if it's a data frame. And so I similar sorts of things to read.table or read.csv in terms of is there a header, what are the names of what are the types in the different columns. I'm not sure if this is required, but particularly for big data sets, it seems like this would be quite important for having it be able to more efficiently work with the data and someone's reading it and not have to be guessing what the types of the different columns are. So using some of, I guess this is still taking a while to work its way through that column, but I basically figured out what were the types of the different columns and then said explicitly what types to read in, or to read it in as those particular types. And in this case, I was careful to make sure that I had the file on the local disk of the machine that I was working on, because I don't want to be, it's already going to take a while to read in 12 gigabytes, to read that in sequentially into R and format it and basically write it out into this new type of file, this binary file that I mentioned before. I don't want to be doing that in addition, on top of that, having to transfer all 12 gigabytes of that over the SCF network as I'm in the middle of that process. So I transferred that first in one copy, and then it was sitting on local disk. Okay, so when I did actually read the full thing into R, the 12 gigabytes, it took about 40 minutes, so not inconsequential, but doable. And then what I did was so this is basically, when I say read it in R, that's maybe sort of a slightly bad way of describing it, because it's not, the whole thing is not sitting in memory on R. Basically what it's doing is it's processing through the CSV file and writing a binary representation of that out onto some temporary location on disk. And if you look behind the scenes, what you'll see is that it's writing it out in /temp and then some R temporary directory, like /temp/RTZ5736, some temporary name for a directory, and it's writing out a bunch of files there. But we can also explicitly save the this FF data frame in a binary format by doing something called ffsave, and that's going to save a file that's called airlinedataall.ffdata. And it'll also save a little bit of a small amount of metadata in an RData file as well. So I took the time to do this ffsave, and that took a little while, and that created these two different files. And once I did that, those were much smaller than the original CSV. So I'm going to look at each of these files. So this is the original 12 gigabyte CSV. All right, yeah, 12 gigabytes. And then here's the FF data, the binary compressed representation of that, and it weighs in at 1.3 gigabytes. So there's quite a bit of savings in using this format. And then the nice thing is, in addition to getting the data storage being more efficient, I can then read it back into R such that R is then able to, and again, I'm sort of using sort of Lushtan terminology in the sense of not reading it all into R's memory. I'm just sort of setting it up for, it just sort of sets it up for R to then work with it. If I use this FF load, that makes it accessible to me in R, that only took, say, 2 or 3 minutes to do the loading, whereas it took 40 minutes originally to read in from the CSV.
Question.
Yes?
So does this kind of mechanism make sure, guarantee, no matter how big the data really is, I'm going to be able to work in R with that, with this kind of compression and more?
Yeah, I mean, yes and no. I mean, I guess there are two constraints. One is that as it gets bigger and bigger, I said it took 40 minutes to read it, and it's just going to take longer and longer. So it's whether you have the patience and time to wait for that to happen. But the other thing is, of course, it could get to be too big for your disk. And in that case, you're going to have to start thinking about mechanisms for distributing the data across multiple machines with multiple disks or some sort of much more complicated file system. So,
How about the core memory I have?
Yeah, so this should be quite efficient in terms of working with memory because it's really working with chunks of the data set as it processes it. And when it goes to when it tries to do subsetting or doing a linear model fitting or whatnot, it's basically getting the stuff off of disk in pieces, working with it, and then getting the next chunk. So memory should not become the limitation here. What should be the limitation is basically time and disk space. Okay, so let me just say another couple things, and then I'll let you guys go early. So when I do the FF load, it prints back something that looks like this, which is basically telling me, for some reason there's no slash here, but this is indeed /temp. It's basically storing stuff temporarily in files with these names. So you sort of need to be cognizant of the fact that you need enough disk space in wherever it chooses to put those temporary files that it doesn't run out of disk space. So in this case, that there's enough disk space in /temp. And then I can start working with the fields in the data frame, in this FF data frame, in the usual ways that we're used to working with data frames in R. So I can start looking at individual fields, or I can start doing other sorts of queries, like I could use the FF analog to table to pull out the individual elements of the destination. So these are different airports. So why don't I quit there, and we'll come back to this and actually running a couple regressions on this data set on Monday. And remember that we've asked folks to do a little bit of work in advance of section on Monday, and that's due. Your response to that is due at 9 a.m. on Monday.
Can I ask a question about setting up SH server?
Setting up what?
SH server.
SH?
SSH.
Oh, SSH, yeah.
So I have a PC at home, and there's a router, and I want to set up a SSH server on that, and I want to access that from internet.
So you want to SSH into your machine at home?
Yeah. And when I set it up, and when both of the
Actually,
computers...
hold on 1 second.